Tonight we're going to speak about how to basically get something out of nothing, which sounds pretty crazy. And the situation is like, what do you do when you're trying to use the data science methodology on something where you don't have a lot of data to fit with, and you don't really have labels, but you actually need a specific kind of label. Now, before we start, I'll introduce myself a little bit. Don't get too excited, by the way. This is not going to be like a talk on Eastern philosophy with all this words of nothingness and Zen. But my name is Jeffrey. I have a PhD in mathematics. I did a master's in mathematics, and at once upon a time, I used to work at Goldman Sachs when I was more of an evil banker kind of person. So what are we going to discuss? Well, we know essentially that data science is driven by business, products, solving problems for people, and we use data to do that. But what do you do in the situation where it's scarce? And what do we do where like the usual methods, because they don't really work so well, you know, when we set it up? Because often with a data science method, we're not really trying to, we're not often really trying to deeply understand the structure of the data in the sense of like where it's being driven from. We're using an algorithm in order to extract meaning from the data empirically. Sorry, I'm not good with the mic. So what do we do in the situation where we take our data, we apply all of these wonderful things, and we get nothing out of it or nothing useful out of it? So in the case, for example, where let's say we're trying to fit a data set where we don't have a specific label, right? And I would remind you, when you do clustering or one of these other, unsupervised methods, you are looking for a pattern in the data. You're not looking for the specific pattern because you don't have it to look for it. So in this situation, if you want to estimate or evaluate a model, you probably need to come up with a way to at least philosophically understand how good it might be. And in that case, you would come up with a proxy data set, a data set which you at least believe is similar to the data set you're using. But whether or not this is the actual error, right, when you measure it, sort of your best case sort of way to go is to try and pick a proxy data set with the weakest possible assumptions of how they might relate. In other words, in the first case, like where the means are the same, this would be basically assuming the data sets are identical, more or less. And this would be the strongest possible assumption, and something you want to avoid, all the way down to, the data sets or the error in modeling is at least similar, all the way to, well, maybe the distributions of the error between the different methods on the different data sets might be similar. And this will be the case actually where we set up our proxy data set where the idea is that the error in the modeling should be similar versus all of these other sorts of stronger assumptions we're going to make. And of course, we set up an error evaluation metric, which is just the weighted relative absolute error, which is just weighting, at least in our case, based on installs of the relative absolute error.
The two samples, are the indexes the same?
Sorry. Oh, sorry about that. No. So in this case over here, this is just, if you want a specific example, we would have, let's say 10 observations or campaigns or whatever you're trying to estimate. This would be the estimate of the value. This is the actual value, and that's just divided by it. You can have an issue if, of course, the value is 0, right? So you can tinker with that a bit. If you want to be really fancy, you can use a difference of means or difference of proportions test from A/B testing or from statistics if you're less markety and more mathematical.
Right here, it's the Manhattan cousin of the square.
Yes, basically, essentially. Sorry, I'm really, really terrible with the mic. It's not my one. So the question we're going to ask ourselves is like, what do we do how do we sort of approach campaign performance when it's not observable? And let me explain what that means. As Ron mentioned, at AppsFly, we do attribution, so advertisers can assess where to put their money. And by campaign performance, we'd ask ourselves, well, in this specific campaign, do people actually become paying customers, and how much money do they spend, or how much does each paying customer spend, for example? These would be things that we that we care about. And in general, when we have limited data, we have the day one data, right? It comes through, but the advertiser, after 1 week, wants to know how well things are going. And in some cases that can be invisible, which I know sounds a little bit crazy, but that is the case. So what we're going to do is we're going to build a model where we use the first day to measure the first week. That's pretty standard data science stuff. But what about the ground truth? We just said that, well, the first week's invisible. We don't see it, right? For whatever various reason it is. And this is where we have a proxy data set. The proxy data set we're going to use are campaigns which, using other methods, in the case of AppsFly, Ron mentioned probabilistic modeling, where we can create a ground truth based on those estimates. And then this will be our sort of proxy that we use to evaluate, not to fit the model. We'll still fit the model on the data set we're trying to estimate, but that will be the data set that we use to estimate how good the model's working, to get a sense of how well it's fitting the data. That's really unfortunate. Okay, so that's very embarrassing, by the way. At least somebody could laugh a bit. That would make me feel better. Okay, so I'm going to quickly speak again about what's attribution, although Ron did bring this in. So essentially what attribution is when somebody serves an advert or clicks on an advert and then installs and then makes a sale, makes a purchase. We want to marry these things together. We want to find a way that we can attribute them, from campaign to campaign. Now, why it's complicated, again, it's since iOS 14, if you have an iPhone, you'll notice a lot of times, unless you actually directly consent to giving the data, we don't see that. But in general, for many sources, we can still get something where your privacy is still maintained, but probabilistically we can estimate that. But there are cases where we don't even get access to the very basic data in order to do that, and that is the case of an SRN, or a self-reporting network. And this would be companies we all know, like Facebook, Twitter, and Instagram. Well, I guess Instagram is Facebook, but anyway, so. Sorry?
I'm not sure Twitter is still.
I haven't spoken to Elon in a while now. I'll have to give him a call and see how things are going with that. So the way we started off, like all good data scientists, right? We have a whole bunch of campaigns and we want to fit some models, but we need to create the observations, right? So one way you could do it is you can take all of your apps. For each app, you can split your campaigns into your training campaigns and your test campaigns. You can then fit the model, right? And then get your output, right? The only issues you're going to run into is one, when you create that model, you're going to create that model on the consented data, right? Sorry, on the probabilistic modeling data, and then assume that that's going to work well on your non-probabilistic model data. And we are, like you see, we're now bringing in assumption number one. The means are the same when we do that, right? And that's something we don't actually want to do. But even worse than that, because campaigns can vary quite wildly between each other, when you sort of select your training and your test, like the actual fit to the model can, first of all, be very volatile. Even if you average out, you can get quite poor results. So that doesn't work. And also you'll see we aren't using all of the information. Now there's something I did not mention. Even though we cannot see for the installs and the install data how to attribute it exactly, we can see which users actually made purchases. We just can't marry them to a specific advert, right? We can't do that. So what that means is at the app level overall, we could estimate that, right? We can exactly see what happens on day one and exactly see what happens over week one. So you might say naturally, all right, let's do a time series model at the app level. Let's fit a regression on that for those parameters. And then let's see how that model will run on the data itself. Now, at least here, one, we're not mixing potentially data which has probabilistic modeling on it versus data which does not, from SRNs and non-SRNs. And the other sort of strength of this is that it's on the data set itself, right? So it has a sort of purity when we do that. The only problem is that once you're at the app level, you've got so many installs and so many conversions and so much revenue occurring. I know a lot of revenue, fortunately, that it's very stable. So you're now fitting a regression on really stable data. You're going to get nice relationships. You're then going to put it on the campaigns, which are really volatile, and it's going to fit terribly. So in both cases, you'll sort of get a model that just doesn't work, right? So this idea of trying to use the thing we care about as the observation doesn't work. And this is where it becomes complicated, or maybe more interesting in terms of that. So we got a little bit of inspiration from like the cinema, the movies. I don't know how much you look at Box Office Mojo. I'm sure everybody has seen a Marvel movie probably at some point. And one thing you'd have noticed if you actually looked at the data is like the first weekend, the numbers are massive, right? And then afterwards they like drop off quite quickly. And if you've actually looked at they have some cinema level data as well. Like in a lot of cases, you actually see a fair amount of similarity in terms of the amount it drops off. Some cinemas might have higher attendance than others, but the sort of relative drop off has a certain similarity to that. So we started thinking, well, maybe we can think of our users and people who install in the same sort of way. The people who are the most enthusiastic about the app, well, they'll spend money like in the first day right away. And then we'll see after this like initial period of excitement will burn off, we'd have like a second phase where people maybe are less enthusiastic and have less conversions. And maybe if our data allows us, we can use this idea that the drop-off could be similar across all of the campaigns to extract a way to link week one back to day one.
Maybe you mentioned kind of saturation model.
Yes.
So but the application, I'm not an expert on application, so maybe I'm wrong. Sometimes it's kind of doing badly, and then for some reason it started.
Oh, you mean you get the reverse phenomenon? You mean like instead of selling down, it sells up?
Yeah, because in first, like when you first have an application,
right,
and let's say you're having a chat application, you're the only one, none of your friends has.
Right, no, exactly. So in the sort of methodology one can approach can actually handle both cases. It sort of doesn't really care whether things start off low and go up or start off up and go low, except if you have stuff that's wildly inconsistent, where in some regions you have like reverse phenomena. This can be a lot more complex to model. Fortunately, we haven't really seen that in most of the sort of instances. But you're right, we do have some clients, I'm not going to say who, where actually on the first day it's lower and then it does go up on the sort of daily basis. So the sort of approach we're going to take will fit that into the data. It will be baked into how we approach it. So this is, by the way, the important thing to sort of understand. So I need to focus as well, I'm afraid. So what we're going to do is this, right? We're trying to essentially model a basket of users. A campaign is a basket of users. So we're going to create a model to describe a single user. And then when we fit that model, what we would usually do is estimate quantities from that basket of users. So if we think of the two different phases from day one all the way to week one, and we think of the customer making purchases as Poisson arrivals, if you're not sort of familiar with the Poisson process, you can just think of this as, the time from the install, and this is kind of like the force of the event occurring over a very small period of time. We'll go into a tiny bit of the mathematics later, but you can just think of this as being almost analogous to like what a probability might be like over a very, very small period of time, how it works out. Now, you see, if we could estimate both that and that, there'd be nothing to do, right? Because we would have the answer. Now, we have this one over here. So the idea is that, can we create a model where we can extract that from our campaign level data, find a link to link from here to here at the app level, and then from that extract out an estimate for that, and then we have both periods covered. So you can think of it as like starting off with the campaigns, projecting down into the users, finding a link from the user over the first period to the second period, and then projecting back up into the campaign data. So the way, if you want to think of this mathematically, is we have our first estimate that we're mapping to our second estimate. And then we have the sequence where we take the estimate to the model, from the next model to the second week model to the second estimate. This is exactly that. Here we can think of this as our parameters that we're estimating. And then we can set up the mathematics of it where we sort of invert the first model, link to the second model, and then project onto the final model. If you're familiar with things like encoders and transformers and that sort of thing, you'll see it's an analogous process where you transform your data set, you then map it from one space to another, and then you apply the same thing. Now, the question is like, is this a reasonable process to do, right? Like, is this something where, like, we're gonna set estimates equal to equations? And one thing we can remember is that in statistics, often when you estimate, we use something called the maximum likelihood methodology when you calculate these things, but you can also use method of moments for extracting parameters. And the one thing that we know, even though method of moments doesn't have the same sort of, I guess, benefits like UMVU and that sort of thing as the maximum likelihood methodology does, it does have the benefit that as your sample size gets very big, thanks to the law of large numbers, it will converge to the actual expectation, right? So in a sense, it's quite reasonable to set up this idea. And this is where we have our, in a sense, probability that the person converts over the first week, which is just the expectation of the binary event that it occurs, which we set equals to the estimate, which is the proportion of people who convert. And this is the thing we're actually interested in. So, as I promised you, we'll just do a little bit of math to kind of see where this model comes from. If we think back to this period where we have this, like a probability of conversion over a very, very small period over here. And to derive the equation for this, right, the probability of a conversion over the first interval, well, this is just the same thing as adding up or integrating, depending on how loose you care about the mathematics. This is a bit heuristic. Please don't go crazy with the measure theory and how this thing should be defined, but you can think of this as being, what's the probability that the event does not occur in the first initial period, and then just at the next little bit, it occurs. When you add this all up, it's the same thing as covering the event that the probability, covering the probability that the event occurs over that period.
0 and x.
Yeah, so over here. So it's saying like, what's the probability, like if x is, let's say 1 for day 1, that's what's the probability that the person converts over 0 to the first day, which is the same thing as adding up over. I guess you could complain a little bit that I've used X here and I should have maybe used a U or whatever, you know, for that. But anyway, nobody's perfect, right? So if you take this equation and you differentiate it, in the differentials you get a very nice formula from the exponential distribution. And this, of course, is actually a very well-known property of Poisson arrival processes, that the arrival times have an exponential distribution. And you'll see, like, for example, this lambda s over here, that will have, let's say, one value on 0, 1, and then another value on 1 to 7.
Can you repeat what does 0 stand for here? Like, what do you mean by converts to 0?
So I guess the conversion time. So conv here is the conversion time is in that interval. So here conversion is the time that the person actually will convert from being an install into a paying customer. So a very simple example is like you install the app at like midnight because you can't sleep, right? And then at 2 a.m. you pay for coins on the gaming app. And so your conversion time is, I guess, 2 over 24, right? 1 over 12 in that one over here. So it would fall within that one. Is that clear?
Yeah, but why 0?
Yeah. So, okay. So if we integrate out, we get that the probability that the conversions occurs up until the end of the first day is 1 minus x negative lambda 1. We get the probability that the conversions are less than day 7 is 1 minus x minus lambda 1 minus 6 lambda 2. Here we specifically specified lambda as a daily value. That's why we have the 6 over here, because we want, it's one of the things in data science, whenever you're playing around with your data, the more consistent you can make things in terms of how you can compare them from period to period, the stronger your models will be in general with that. And here is going to be our link value, right? Because we know what the lambda 1 is, because we can just set this equal to the conversion proportion on day 1 and solve for lambda 1. But to get lambda 2, we need a link to that, this k value here. And the way we do that is by projecting then from the campaigns up to the app level, okay? And then we solve for the k value at the app level because we have all of those observations, very simple mathematics. And then that pops out with our value for lambda 2. And so we can now estimate everything for that. And in terms of like, you might ask yourself, like, how does this methodology like compare, right? Well, we found that if on the data set of, I think it was something like 1,500 apps, about 3/4 of them had at least 80% campaigns with less than 20% error in the calculation, or using the error metric we referred to at the beginning, the weighted relative absolute error. It had a weighted relative absolute error of less than 10% on average for all of the apps. But one thing to remember, this is like a proxy evaluation because we're doing this on the data with probabilistic modeling, right? So this is not the same thing as the actual error, because the actual error on attributing the campaigns is impossible. I mean, only God knows that, or if you don't, depending on your beliefs, right? It's not going to be knowable at any point in the future. So we're sort of working on the basis that something should be broadly comparable in that respect. So, you know, one thing I did mention is that not just conversion, but also revenue, right? We wanted to look at the revenue per user. So how do we do that? Where's the money, right? Well, we can approach this in exactly the same way. Again, we model the user, and we then have the user starting to spend on each of the specific days. The one benefit is we already know we can already estimate what's the probability they start spending money on any given day, so we can break things up that way. All we have to do is estimate if they start spending on day 5, how much are they going to spend, and find a mapping for that. And that's exactly how we set it up. The expected revenue, given that they're paying user, will be the probability that they start spending on a given day, times by what the expected revenue is from that given day, given that they're a paying user. We can generate the formulae using the mapping we have from P1 that we get on the first day, probability of purchasing on the first day, and calculate using the formula from the Poisson arrival times. For the second part, for the revenue, this is a little bit more complicated because the revenue is going to be the number of days times by the average daily spend, okay, over the second period, which is not directly visible, right? But we're going to have the same sort of methodology where we look and say, well, maybe we can model things with the average daily spend being some multiple of the average daily spend on the first day, right? And we can extract that by trying to do it at the app level in terms of extracting that. And then with a lot of algebra, which I've spared you, so you can thank me for that, even if you wanted to see it. Yes, it's like, have you ever seen like in all the computer science textbooks, it's like the first thing is they give you an example where like, it's like write a program to add 2 numbers together, and then the exercises are like solve the Riemann hypothesis numerically or something like that. But basically you can extract out the same kind of formula playing the same game. It's just a little bit more complex. It's just a little bit more algebra and how you do that. If you're really that interested, we can discuss it, or you can even potentially come and work at AppsFly. It's an incentive for you to come. So what can we take away from this? So far, this has been like a very interesting case study, right? But you might say to yourself, it's very specific, you're using random processes to model things, maybe it doesn't quite apply, right? Now, one thing that we did find is that if in the case of conversions, we applied this transform minus log of 1 minus x, and we just apply a regression, you can actually get fairly similar results. They're a little bit worse because this model underfits a bit. Because remember, whenever you fit a model with more observations than there are parameters, well, one, you do get robustness, right? You can generalize, but also you underfit in a sense, right? Now, whether or not you're underfitting reasonably or not, this is a whole other philosophy, right? But the point is that you could have got something relatively similar just by applying this transform, right? And so what I want to point out is that by thinking about something structurally, that can help you see what your feature transformation might be. You don't necessarily have to build out the entire model and do everything. You can just try and think about how the different variables are related to each other from a structural model, which will tell you what your transformation needs to be. And what that means is that by thinking this way, you can actually do feature engineering the easy way, right? Well, okay, maybe the easy way is a bit of an overstatement, the easier way. And the other thing that, other than subject-specific knowledge to do a bit of feature engineering I want to mention, is that you'll notice when we convert those probabilities into lambdas, these things look awfully additive in the model, right? You notice we add lambda 1 and lambda 2 together because in that space it's additive. Probabilities are not additive, right? Probability of two events occurring, you can't just add them together. So when you're going to take features and you're going to chuck them together in a model, look to see how you can transform them, even if it's not necessarily structural, but to transform them so that they live in the same sort of space as each other. So relative to each other, they might vary in a similar way. They might have the same kind of bounds. They might have the same properties. I don't mean transform the one into the other because, well, then you get nothing, right? But transform them so that they can become comparable. Because even in things like regressions and in certain kinds of networks, whenever you take linear combinations, if you mix together things that are not really consistent with each other, you don't necessarily get a good result coming out of that. And on that cheery note, thank you. We made it to the end. Thanks, Bob.